All right, so the day an asteroid nuked the test site. It sounds like hyperbole, but it's actually not. And what I'm hoping, I'm going to take you guys on a journey. This is what the talk will look like. This is for those of you who want to peek. We already went over this. We have background in geology and space, and that's why I'm talking about space geology. Worked at Bigelow Aerospace for a while doing radiation safety, and now I'm back working at the Nevada test site, now the Nevada National Security Site, with radiation control, a radiological engineer. So welcome, everybody, to the second annual Asteroid Day. And this is, Asteroid Day was started by, it was actually, there's a lead guitarist at Queen who you may have heard went back and got a PhD in astrophysics. It's true. And he partnered up with a couple of heavy hitters to try and bring global awareness to the idea that we need to be doing more to prepare in case an asteroid hits us. So it's pretty straightforward. And a lot of people are on board, even more this year than last. So major institutions, Museum of Flight, Discovery Science, Astronomy, you name it, and a bunch of people are jumping on board. So Bill Nye and Neil deGrasse Tyson came out and have endorsed this and are promoting this. So I said this last year, and you'll forgive me for punting it again, those of you who were here last time, but I think Asteroid Day can be summed up by a great Larry Niven quote, which is basically the dinosaurs went extinct because they didn't have a space program. And if we don't have a space program, we'll go extinct too, and they'll serve us right. Because basically we saw it coming. We have evidence nowadays. So why June 30th? And I'm going to try and dodge and move around some of the content from last year so this isn't recycled. I don't think I mentioned why June 30th. It's actually the anniversary of the Tunguska blast, which is the largest asteroid or comet impact in recorded history. We've gone back, even though there's no meteorite sitting at the center of the impact site, it looks like it was an asteroid or a comet that exploded. It came in really fast and didn't actually hit the ground, but it made a tremendous explosion, many thousands of times what went off in Hiroshima, and it leveled more than 1,000 square kilometers of forest. And very mysterious, and there are reports for hundreds of miles of people hearing bangs and then feeling a gust of wind, so all the indicators are there. So that's why June 30, it's the time our awareness began that maybe we should be thinking about this stuff. And what I thought I'd talk about for a second is asteroid basics. I think anyone coming out of an Asteroid Day talk should know a little bit more about asteroids than they did before they went in. So what is an asteroid? It's basically leftover is junk from the early solar system, when the solar system was forming. And they come in a range of sizes. Most of it's very small, a little bit is very big. So, for instance, 433 Euros is 10 miles in diameter on average. Vesta is a big player. We've had a lot of research going on here. It's about 330 miles in diameter. And all the way up to the King, there's Vesta, there's Eros again, Ceres, which you may be aware used to be a bona fide planet. So it was the first asteroid discovered, and it was actually named, and it sat right in the pattern. And much like what happened to Pluto, when they found that, well, Ceres was sitting amongst many, many other small bodies right near it, they demoted it to the king of the asteroids. So, like with Pluto, they've discovered more and more worlds, more and more objects, and so now it's one amongst many, but, king over there. So one of the interesting things is we now know that the asteroids that are out there, and we learn about them based on the meteorites that fall, most of them come from asteroids, there were at least 80 distinct, they call it differentiated worlds in our solar system's past. 80, that's a minimum number. I was shocked to learn this when I started doing graduate work. The geochemistry, there are unique fingerprints, basically, to make a long story short. There are geochemical fingerprints that are absolutely diagnostic, and they suggest 80 is a minimum number. So there was a lot of stuff going on in the early solar system that eventually got cleared out to leave the big ones we're familiar with today. But when they say differentiation, and I'll try to keep the jargon to a minimum, that means this process is depicted right here. So you have little bits of rock that come together based on gravity. It's just a rubble pile. But if that pile gets big enough, it starts to heat up in the center. And then it will start to melt. And just like anything that is fluid, the heavy stuff sinks to the middle, and the light stuff floats to the top. So worlds, when they get big enough, all of them will differentiate into a core, a mantle, and a crust. So that's what they mean. So when you see a round world, that means it's differentiated. So it's got some manner of core, mantle, and crust. Well, this relates because there are basically 4 types of asteroids. And there's a whole language of this stuff. I'm going to bypass all of it and boil this down to basics. You've got stony iron, and then raw. And how we can link that is, well, guess what? Stony means crust. So if you find a stony asteroid or a stony meteorite, it's basically basalt similar, and you're looking at a piece of the crust of one of those ancient worlds. Stony iron? It's in between. So you're looking at mantle core boundary. You may see meteorites like this that have these wonderful olivine crystals in them that are transparent. So you're seeing an intermediate. And then iron is the core. So if you have an iron meteorite, you're looking at the ancient core of a dead world. It was blasted apart, cooled off, solidified, and was blasted apart. And then finally, if none of that ever happens, there are a few asteroids and then meteorites that we found from the original stuff that never melted, just collected together, and you can actually see that reflected in the rock. It's actually a collection of a bunch of tiny little spheres, all stuck together, and just as you'd envision it, a bunch of little clumps stuck together that eventually lithified. And there you go, 4 types of asteroids. Stony iron, and raw. So I have to make mention, we need to justify Asteroid Day, so why should we worry? And I spent a great deal of time on this in the talk last year, so this year I'm going to land on a different point. There's lots of material that strikes the Earth. Every time you see a shooting star, that's basically the Earth, because it's moving around the sun. The Earth slamming into something, or something slamming into the Earth. And the exchange of material is appreciable. There's on the order of 7 or so Volkswagen Beetle cars worth of stuff that hits the Earth every hour. So what made us alarmed? So starting in the 80s, we actually started recognizing evidence of major impacts here on Earth. We look at the moon, and the moon's been hit by a lot of stuff, and we're bigger than the moon. So logic suggests we were also hit by a lot of stuff, but we didn't see it until we started developing technology to look deeper. So the crater that's related to the dinosaur extinction, Chicxulub, it's about 100 miles wide. That's pretty significant, 65 million years ago. And how do we find it, really? Geophysics. The crater's not sitting out there, but what people found is when you started measuring the density of the rock, a pattern showed up. This double ring thing. And these little white dots, I know they're hard to see. This is from a study that linked, there are a bunch of sinkholes. And the sinkholes happen to follow the rim of this crater because that's where things were compressed. So you talk about a smoking gun, it's a buried crater, but we found it, and it's huge. Chesapeake Bay. A few people know that that's a giant impact crater. And again, you can't see it on the surface, but this is its shape. It's double ringed, which means it was a big one. So small craters, just one rim. Big craters have multiple. How do we find it? There's a density map. Again, geophysics. So our ability to technologically probe what's going on under the ground or within the ground. And then Chelyabinsk, in 2013, many of you are aware that a meteor went over the top of this town in Russia, blew up, and it blew 20 miles up, and even from there, it damaged 1,000 buildings and injured 1,200 people. So if you imagine the force necessary, they worked backwards and found it was 50 Hiroshima bombs that went off 20 miles up. So if that had actually hit the town, that would have been a really different kind of tragedy. What I wanted to show you that's cool for here, since we're at the Atomic Testing Museum, is you'll note that the bolide, that's what they call a meteor while it's burning up, it struck in and then blew up. There's a point during its track where it really heats up and explodes. Well, if you link that back to the contrails that it left behind. There's a lateral mushroom cloud. It's one of the coolest things I've ever seen. If you see video, this is a mushroom cloud that's rising from the point of explosion, and actually it's fragmented, so there are multiple tracks. So imagine a series of nukes going off this way in the air, and then it's sucking in the air and rising, and it's very interesting looking. Well, that's great. But what about us here in Nevada? Is there anything we should care about? Why should we care about asteroid hit here, hypothetically? Because if you roll the dice, the Earth is big, something probably won't hit here. Well, is there anything closer to home? That's what I started asking myself after the talk I gave here last year. And the answer is yes, and it's a big yes, and it's one that surprised me. So I want to talk about what I'm calling first the Devonian Discovery. So in the 90s, geologists found breccias here sprinkled around some of the lesser populated areas of Nevada, near the town of Alamo. And they called it the Alamo Breccia for that reason. And just so you know what we're talking about, here's an outline of Nevada. Here's Vegas. There's the first point of interest. And what you're seeing here is just how tortured Nevada is, basin range. These are all ridges. So the continent's been crushed and accordioned, and that's destroyed a lot of evidence of things that are very old. And this is what the breccia looks like if you slice it up and polish it, so you can see. So this is a rock, a breccia. It's like a conglomerate for anyone who's heard that in geology parlance. It's a rock made of other rocks. But what makes a breccia different is its sharp. These are angular little pieces, whereas a conglomerate tends to be composed of eroded bits. Like if we walked around in the washes out here, they're all round, pretty spherical. It means they've been outside a while. A breccia, which you can find on a fault line where earthquakes happen, something happened quickly and shattered the rock. And then it got lithified again before it was exposed and had a chance to be, turned into a conglomerate. So these rocks are really ancient as far as these things go. So geologists have named periods of time arbitrarily, but there's its own language. All the sciences have their own language. So I'm trying to keep this down. But around 380 million years ago, there's a time called the Devonian. And because it's so long ago, there are very, very few rocks that are exposed from then. They've been reworked, pulverized, buried by volcanic eruptions. So in order to understand the breccia that we found, I thought it'd be a good opportunity to take you out of time. And the Earth, when you start thinking about deep time, which is what geologists refer to as the span of time since the Earth formed to present, you get familiar with the idea that the Earth's had a lot of forms. It's actually been very different throughout its time. And this is what we're used to. I pulled a Google Earth image. But if we want to understand what we're finding from back in the Devonian, we have to understand what was going on then. So I want to give you guys a Devonian view. And I don't know if can you guys see okay, or should we switch to the other lighting scheme? Is that okay? Okay? Oh, it's okay. We're good. So this is the world as we know it, and what I want to do is take you to one specific other moment in time, the late Devonian. So not this Earth, but this Earth. Welcome 380 million years BC. And there's one guy in the country who does these maps. His name is Ron Blakey, and the amount of research that goes into this, he takes all the other geologists' work where they find evidence at a certain period of time. Well, there was a coastline over here, and there was a shore over here, and it was deep ocean over here. He puts this all together and creates these masterful maps that are technically accurate, and I have no idea how he has the time to do all this, but they're amazing, and everybody uses them. So this is what the Earth looked like, for all intents and purposes, an alien world. And they have names, so geologists can talk about it. So the continents at the time, we're going to talk about Euramerica. There was Gondwana down near the South Pole. There was nothing near the North Pole. And so you can track the land masses that would one day come to be more familiar. But this was the world then. But then again, I don't expect everyone to just swallow that. So how do we know that? You don't have to take my word for it. There's actually a really straightforward story behind how do we know that that's what the Earth looked like a gajillion, bazillion years ago. We weren't there. Well, it's a very interesting story behind that. Mid-ocean ridges and there are a few different angles, but this is the one I think is most important. Magnetic lineations on the seafloor is what they call it. So you may be familiar that across the Earth, in the middle of the sea, there are these ridges, and they're mildly volcanic. So you've got thermal vents. There's new crust being formed. We're actually getting farther away from Europe every year, 1 millimeter. So over a decade, you move a centimeter. Over a human lifetime, you can measure how much farther away it is you are from flying to Luxembourg or something. So this is what it looks like. You end up with molten material coming up, hitting the water, cooling off, and forming new crust. It builds up, and it pushes that stuff apart. You end up with these spreading centers. Well, something else that's true is we know the Earth's magnetic field has flipped over time. And when you put these two things together, what you end up with is patterns on the seafloor. So the orientation of the magnetic field, just like when you make a magnet by stroking a nail in one direction, you align it. Well, when these rocks are molten and then cool, it solidifies the orientation of the magnetic field in that rock. And it can't change unless you melted the rock again. So you end up with symmetric stripes on either side of these ridges as the field went one way and then the other way, one way and the other way. So it's a map of where the continents used to be. And what you can do, a lot of work has gone into mapping it. So just, you can see that there are lots of stripes going on here. This is a seafloor map, magnetic seafloor map. And they found multiple layers. So when geologists worked backwards until all the stripes came together, they found another series of fainter stripes underneath that had been, sort of like a Rubik's Cube, that had been hidden because they were split apart by the new ridge. And then they put those back together, and then they found an even fainter one. And so you're reaching farther and farther back in time, but it's telling you exactly how plates moved around the Earth. And so if you collect all this data like a jigsaw puzzle or a couple layers of jigsaw puzzles, you can know where the positions of the continents were. So I just wanted to take that as well. There are other tools too that you can compare. Well, when two continents were supposed to be together, do you find the same life forms there? And yes, and there's a bunch of double confirmations that things are different until suddenly they're together and then they're the same. So it all starts to make one story. So now back to the time we're worried about. What about the Devonian? Well, this is a time that we don't hear about. There aren't Devonian Park movies because it wasn't, frankly, all that exciting for us. But what happened then, this is a world that I want to really take you into because the Devonian was very important. It's when plants really moved onto land. And then by the end, over the course of a few decades of millennia, or a million years, so you get from 419 million years ago to 358 million years ago, what happened was plants populated the continents. So if you were in a spaceship looking at Earth, at the beginning of the Devonian, all the continents, we had no green world. Continents brown, gray, sort of like the moon, Mercury or something. And plants moved on, and then life followed of estuaries. And so what did it look like? A really alien world for us. Nothing like the Earth we know. So the kinds of plants that first moved on the land didn't work like the plants that we have today. And I'm not a biologist, and I'll admit that. But they were much cruder. And these spires were fungus. They're fungi spires that thrived in this environment. You had weird trilobite-like critters that were moving up, freshwater creeks and things like that. And once plants really started to take over, they're still different than what we see today. So you call it an ocean world, ocean and a plant world. Not much going on land. And the animal life that was going on here, it's predominantly fish. You had bony, armored fish that we'd never see again after they went extinct. Weird stuff. You had the beginnings of fish that would become amphibians. But really, people call the Devonian the age of fish. Like this monster here, this is 30 feet. That's a human. This is all armored bone. So I just wanted to paint you a picture of, envision that world. And that's what we're reaching into. So when, I'll get there. So where was Alamo then? Now we're in the Devonian, we're in a spaceship floating over Earth, we're looking down. Well, it was here. So not up here where we're used to. It was actually down in the south latitudes, about 15 or 20 degrees, and it was in a coastal region. And you might go, huh, coastal. Well, I notice I see fossils when I go hiking at Red Rock, or I see the big sandstone cliffs. Well, the sandstone is a beach. The big angled waving lines, those are dunes. So now you're sort of diving into this region. So we zoom in, and we've adjusted it, and I don't know if you guys can see it, but there's a faint outline of the United States here. And here's Nevada. The west half of Nevada doesn't even exist yet. And we're tapering from like the Bahamas to very nice, shallow blue water, white sand. And it's diving off as you move to the western part of the state down into deep, deep ocean. And that's Alamo. So try and visualize that. So the Alamo breccia indicates an enormous sudden event. But what? So through the mid to late 2000s, there was a lot of skepticism. If you propose something like an impact, the core group of people who came before who didn't think there was an impact are going to fight it, and they did, but then they started finding things like shock quartz. It's fractured from something like an explosion. Lapilli, which are literally fire bombs you usually see coming out of volcanoes, but they can also come out of impacts. There's tsunami deposits that happen at the same time, so clearly something really disturbed the water. And there's also an iridium anomaly, which iridium is a rare earth element that tends to hitch a ride on material that comes from space. On Earth, it differentiated and it's not really accessible on the surface. So this is a picture of the Lapilli. And this faint, where this arrow's pointing, this faint circle, you have little things that are flying through the air, aerodynamics, and are collecting material that's been vaporized. You pretty much only find that in an explosion, either volcanic or extraterrestrial. So over time, and again, this is fresh, we're in the 21st century, the mapping became more sophisticated. And this is called a stratigraphic section, but it really just means it's a vertical map of the types of rocks in an area that you're going to find. And they started mapping the Alamo breccia. And they figured out, this is the Alamo breccia. It actually comes in different zones. So there's a period where there are small bits and giant chunks, and then small bits again, and bits that fine upwards very smoothly. And that tells a story. You know, you get tools like that, and that's going to take you somewhere. And what it did, basically, there's only one hypothesis that can produce all of that stuff in the Alamo breccia. When you have an impact, you end up ejecting material, you create a water spout. If you have an impact over shallow marine area, which is a continental shelf, you have a tsunami, you end up with tsunami deposits, you end up with several layers of fractured breccia, and then things settle down, and you get slowly calming kinds of rocks. So conclusion, okay, it was an extraterrestrial impact. I don't think anyone's really debating that anymore. But how big was it? Fair question. We're reaching way back. So finding the crater, this is no small challenge. Close to 400 million years ago, how much evidence is honestly going to be left? And of that, how much can we actually get to? Not much. So you're looking here at, this is Nevada, Vegas is right here, Alamo's here, and each of these little circles are the single spots where researchers have been able to find evidence of this, the breccia or like a tsunami deposit. Reaches as far down as Frenchman Mountain. There's a tsunami deposit from this impact on Frenchman Mountain, right over there. And so that became a hunt. Now, not just to map what was there, but to connect the dots and figure out what the crater was. And which, again, this is a picture of Las Vegas. These stars are key expression points for this breccia, so key research locations. And early conservative estimates, based on the thickness of the layers of this breccia, said this, whatever happened, had to eject 70 cubic miles of rock when it hit. So now people getting serious. Like, okay, this isn't just a little hiccup. This is something very noteworthy that happened here. So for context, I'm building this up. Sedan crater, the largest artificial crater on the planet. It displaced 0.001 cubic miles, 1,300 feet across, and it was equivalent to 10 Hiroshima bombs. And this is Nevada, here's Nye County, and that little red dot, that's about the size of Sudan, the largest thing we've blown up. And even that dot's a little big, but I figured people probably can't see that anyway. Now, for contrast, here you go. These red dots are the sample locations, and this line is where the current thinking of connecting the dots and how big this crater actually is. It means the crater looked like that. So, this is awesome. This is amazing. This is a huge crater. I mean, 100 miles across. You know, plus or minus. We're still figuring it out. I mean, you can see, this is a detective story with very little evidence. You can see this like a forensic anthropologist finding, you know, the fragment of a tooth and a thumb bone and going, oh, this was an Australopithecine, you know, and you think, fine, how did they do that? But there are little clues that tell you exactly what you need to connect and take you in a specific direction. So, let's go back to the future. So I thought it'd be fun, now that we've confined that this was extraterrestrial, and we have a rough size for the impact, what would happen if it happened today? So, sitting here in this room in Vegas, how big was that asteroid? We have a sense for the crater size, but we don't know, asteroid or comet. And then how big was the explosion? What would it mean for us? Well, there is actually a rule of thumb that you could take with you, and the object that created an impact is about 25 times smaller in diameter than the crater it made. So you just find the crater size, divide by 25, boom. And it's not, you're not going to win a court case with that, but it'll get you close. So that means our asteroid was about 4 miles in diameter. So that's a decent chunk of rock there that slammed into us. So, considering that Vegas is 150 miles away from the epicenter, which is ironically off the extraterrestrial highway near Rachel, I mean, you talk about the serendipity here, it's pretty amazing the more you think about it, and it only gets better. And I used these parameters, I did a little math. So assuming it was an iron asteroid, going at an average asteroid velocity of a paltry 17 kilometers per second, coming at a 45-degree angle, and we'll pretend that there's still an ocean over there, so the explosion happened the same way. So showering, 30 feet of water sitting there. Well, here's what happens, and I stole frames where I could from what happened over Chelyabinsk. So when the bolide blows up, 6 seconds after impact, you have maximum fireball for this thing. We'll call it Alamo 2. The fireball is 100 times larger than the sun in the sky from here. So if you saw a bright flash and ran outside, there'd be something 100 times brighter, and then you go blind because it's 900 times brighter than the sun. So 100 times larger, 900 times brighter, and there's so much energy being released by this that grass, trees, and your clothing light on fire. So that's not very good. 50 seconds after that, you're trying to reclaim your vision and put your clothes out. A shock wave hits, a seismic wave, earthquake. Magnitude 9.7, something humanity's never seen before. So reinforced buildings may not fall over, but they're going to be askew, and pretty much everything else is knocked over. So assuming you survived that, your clothes are out, and now you're outside of the rubble. 4 minutes later, so we went from a few seconds to 1 minute. 4 minutes, that's when what they call the ejecta. So all of the debris that was thrown up now starts raining down like a nightmarish hailstorm. And the average size of each of these little nuggets here is larger than a golf ball. And then it doesn't let up until there's about 30 feet of it built up around here. So now you're scrambling for one of the buildings that's still standing and that can withstand, 30 feet of rock hitting it. So then 12 minutes, then the sound wave hits, carrying with it a shock wave, and it's actually supersonic wave. There's so much energy, it's pushing the air faster than the speed of sound. It's about 2,100 miles per hour. It hits at about Mach 3. So it's about 123 decibels, which can damage your eardrums, but you're not really worried about your eardrums because all multi-story buildings and the highway bridges are collapsed and cars and trucks are tossed all over the place. And 90% of all trees that are left standing are blown down. Okay, and 7 hours after that, right when you've managed to unbury yourself, and you climb out, and you're repairing your ears, and you're blinking away your vision, then a 6 to 12 foot wall of water hits, and it's basically Vegas is done. You know, we can't pretend anymore. It would be a terrible day. So even at 150 miles away from the epicenter, we're still pretty close for something like this. So to bring this home to the asteroid day portion of this, if you want proof of the wisdom of thinking about something like this, you need to look no farther than just go up to 93, and there's Alamo. So there you go. It happened here once before, right here. So then I thought, well, I want to see this for myself. So the Hiko Hills. Looking at the prime research spots, I picked one. And I thought it would be the juiciest, the most easily accessible, because I was going stomach by myself. So that's it. Just east of Crystal Springs. This is the junction for those who've driven out that way. You turn left and go on the extraterrestrial highway. You turn right and you got to Caliente. So it's right after you turn right, that hill you're looking at. So there's a Geological Society of America came up with a field guide to help young researchers who are interested in this get to it. So I picked up a copy, and this is the mountain in the Hiko Hills that we're talking about. And you're actually looking at the breccia right here. But it's in black and white, and honestly, that was the reason I wanted to get out there with my own eyes, because I can't really tell what I'm looking at here, and I'm a geologist. But they give you a diagram that this is that mountain. And everything that's not this stone pattern, that's, quote, normal platform, just flat mud that's being laid out over time in the shallow ocean, and things are proceeding normally. Everything here in the middle is the breccia. So, if you take that over, everything here in the middle is the breccia. And what you can sort of see is things like this layer pinch out and go away. Well, that's not really normal. And it didn't just get buried, as it turns out. Same thing here. These guys go away. Well, when you start climbing around in here, you find they didn't just go away, they were broken off. They're giant breccias. So I showed you a hand sample of the breccia. This is called a mega breccia. So one piece that was broken off is 800 feet long and 30 feet tall. It was so big, geologists went right by it for years and didn't realize what they were looking at because they were too close. And one guy, his name was Sandberg, noticed in the 90s, well, wait a minute, decided to go up there and check it out. And so what you're seeing here, pieces that are broken off, the little black dots here are where they identified these fire bombs that are captured in there. So then I actually went out there, and I think, I don't know if this gives the intended effect, but like I'm pinching the breccia here when I got out here. So there's the diagram, and so I was standing there, and to bring it home, it helps to see a little bit in color, but there you go, the Alamo breccia. So I hopped out of the car, drove as far as I could take my two-wheel drive SUV, and started hiking the rest of the way. And my objective was to get here, so right in the thick of where this breccia was, according to the diagram. So we're talking, I wanted to get right in here where I can get good samples of all the different types of breccia. Because remember, depending on when it was, different things were happening. There's small breccia and big breccia, and it all tells a story. So I started walking, and almost immediately, geology is a language, the mountain started telling me a story. So remember, we're in the Devonian. You've got this very marine environment. We're in the Bahamas of that world. And yes, this is a smooth, superficial, like tidal deposit. You can see these lateral lines. This is very calm, mud's being laid down. Okay, so we're definitely in a marine environment. And then before I know it, I'm standing on breccia. And geology hammer for scale. This is one of the best expressions I've ever seen. That you've got a rock that's pretty much intact here, and as you look this way, you can literally see the pieces of it have been broken off and frozen in place. So that something was shattered and then buried. And there aren't that many mechanisms that do that. So I keep going. The breccia followed the stratigraphy. I mean, I don't mean to sound surprised, but it's sometimes it is surprising to actually find things obeying, out in the wild, the rules that they're supposed to. So if you ignore the rocks sitting out, but if you just sort of gaze at the average size of the blocks here, they're, a quarter the size of my hammer. But as you move up section, they get smaller and smaller and smaller and smaller until eventually you'd have to get really close to see them. They call that a fining upward sequence. And you can see that in washes right out here, right behind the building, or right up by Red Rock. And what that means, it means that the flow is slowing down. So things are calming down. So I reached the target. I got up there. The view back toward the highway, that's south. Vegas is over a few ranges that way. That dots my Jeep. And only to prove that all good scientists think in the same ruts, I suppose. So I get to the spot I was aiming for, and sure enough, there's a cluster of 12 drill holes where one of the grad student groups or something must have come there and said, oh, this is a good idea. So they drilled a bunch of samples and took them back for analysis. So I felt a little vindicated there at least. And it's just breccia all the way. I mean, I wish, the one thing it did give me is, I wanted to be able to recognize this breccia on site, but this whole wall is breccia. And I know you can't see it from where you're sitting, but there's my rock hammer. And here are big boulders in class, and there are fire bombs and circular things here, and the blocks just keep going. There's breccia up here, and it goes off the top. So, if you wanted any visceral proof, this was an enormous event, and one that people have been just glazing over for years, and it happened right here. So this started to make me very excited, because I think there's a potential for future discoveries at the test site. Big ones. So you might have noticed this looked funny, because all this crater, it's not a hemispherical, it's not a half-circular crater, it's a whole circle. But no research has occurred over here. And, well, there's a reason for that, and it's because that's where the test site is. That's where they've had a test and training range is, so people can't get there. So I went and plotted the test site. So here's the whole test site, and I went and just finished the circle. And sure enough, better than 90% of the site is inside the crater. So the trick then is, are there any spots on the test site where these old Devonian rocks have been pushed up to the surface? So it's one thing to know you're in the right spot. It's another thing to have access to something that's normally 3,000 feet underground. The answer is yes. These two little red dots, it's two spots, Hiko Hills and Mine Mountain, where USGS geologists had previously cataloged sort of puzzling breccias, and this layer is a little thin, and there are a lot of details that go into painting this story. But I think basically there's a story waiting to unfold here on the site, which relates to this and can actually sort of join all sides together of the idea of impacts, explosions, evidence, forensics. And so yeah, basically, I'd like to play with the hypothesis these two sites have been misidentified, and they're just waiting for somebody with access to go over there and take a look with the right pair of eyes on it. So to wrap this thing up, this is a top-level view of the Alamo impact, but I want you to walk away with the irony here. The most heavily cratered spot on Earth, the test site, sits inside an ancient crater. That's wild. What are the odds? It's astronomical. It's mind-boggling. Okay. And then the NSS is an important site for future crater research. And not just the craters that we made. We know about that research, one that happened to be created 380 million years ago. So, for anyone that's interested, I actually grabbed some hand samples. If anyone wants to come up here and actually see the breccia for themselves. And with that, I'll open it up for questions.
Well, a 5-mile diameter chunk of iron should be possible to find.
Yes, that's an interesting point, and as yet, no one has found fragments or the actual ground zero, and that's because it looks like it's west of the border. So, I work out of the test site now. I don't have access to the Air Force side, so it was still, there could be a journey to collect all the bits and pieces to put this together, but you're right. If it was nickel iron and it hit the ground, it's going to leave a mark. There's going to be a deposit you can find. So the only reason that wouldn't be true is if you had a very fine-tuned impact, like what happened at Tunguska, where somehow you had the perfect density of asteroid, not quite as much as iron, maybe it was a comet, that was big enough, it punched down and it created the explosion, but vaporized itself in the process right near the surface. And that's the only time you can get faked out. But yes, all logic suggests there's something out there waiting for us to find.
Same question, but it goes a little bit in a different direction. If you have an impact, then a lot of rocks are molting. So the metal within the rocks will then, in the cooling, go down, probably on the bottom of the stuff, probably 8 miles down or 10 miles, and then should create a higher density
Yes.
of metals. So in principle, there should be a lot of metals like copper, like whatever is in the surface should be on the bottom of it. So it's probably a mining opportunity over there, right?
That's a very interesting point. Yeah, a new kind of placer. So an asteroid generated placer deposit.
Yeah.
Yeah, that's a good idea. We got to get out there. So yes, you're right. That's sound thinking. Yes, let's go look. Anybody else?
Don't forget about the diamonds.
Yes. Well, you get different shock features depending on what you hit.
I was recently at Kennedy Space Center, and on their tour, they were talking about the new rockets they're building to go to Mars. Before they do that, they want to go up and grab a piece of asteroid. And I was wondering, how would they do that and what would they learn?
That's an excellent question. I wish you'd been at my talk last year. I mentioned it just a little bit. It's called, so NASA has an ambitious plan called the Asteroid Redirect Mission, or ARM. And the idea is, well, it's not feasible to grab a whole asteroid, but there are lots of asteroids that swing pretty close to Earth. So NASA came up with a plan to send out, there are many spacecraft that have visited asteroids now, so we have the technology to rendezvous with one, collect a sample from one. Japan did that. And so NASA's plan, you know the Carnival quarter machine arms that reach down and grab them, that never seems to grab the toy that you're after? That's the aerospace version of that is actually NASA's plan. And so there's a robot with a claw. And there's reason to believe that much on the surface of asteroids, as we get more information, a lot of them are rubbly on the surface. So the idea is to simply land, anchor, and grab a boulder, and then secure it, and then take this ship with a big boulder back and park it in lunar orbit. So not making anybody nervous about crash landing an asteroid boulder as a weapon or something on Earth. So to park it in lunar orbit, safe distance away, but easily accessible. We can get to the moon. It's 3 days away. Very close compared to everything else in the solar system. So once it's there, the idea is to take the new Orion spacecraft, which you may have seen. It's like a big Apollo. It's a big capsule, and with a service module, and maybe with an extra habitat on the back, and send a couple or 4 astronauts to rendezvous with this asteroid in lunar orbit. And there are a few reasons for doing this. One is it's the quickest thing that NASA can do, because we don't have a lander anymore to land on the moon, so we can't. So if NASA wanted to do it in the next 10 years, sorry, they'd have to invent a new lander and resurrect all that technology. You don't need a lander to land on an asteroid. Its gravity is so slim, you just kind of park next to it, or actually dock with the spacecraft that's holding onto it. So there's a convenience factor, and then guys can just spacewalk. So then, what would we learn from it? Like I said, most of what we know about asteroids is from the meteorites that we recover here. And there's some good telescope work, and then just a smattering of new satellites that have been in orbit collecting data. But we've never really got our hands on one, literally and figuratively. So we would learn everything from a really good bead on the geology of that asteroid, better than anything we've ever done before. So we will have done that once. But aside from that, the logistics, you talk about Asteroid Day, what will we need to do to stop an asteroid? This is where their mission becomes very important, because when we learn the logistics of getting to an asteroid, manipulating an asteroid, and then we can determine how rubbly is it? Is it really well consolidated or not? We can start applying what we learned from that one to other similar ones out there in it'll help us build out our understanding of what's out there. Because right now it's still very, very coarse. You know, the science is still very new. We've got a lot of meteorite samples, but they're not pure and they're biased. We only tend to find the iron ones. You know, the stuff that's lighter, it either doesn't punch all the way through, or it just gets buried. You find iron because it looks unusual. It rusts and it's heavy. You know, even geologists could step right over a chondrite or an achondrite sitting on the ground that it had some moss on it. Never know. So to really understand how the asteroid ticks, you have to get to one. And so the pure science combined with logistics of how would you maneuver around one. And then finally, we can learn how profitable it might be. You know, if there's a significant component from a real sample of like platinum group metals, which get people really excited, or if there happens to be water hitching a ride as ice on the surface, that's many things right there. That's oxygen to breathe, water to drink, it's rocket fuel, hydrogen and oxygen, you put them back together, boom. I think there's a potential at least to learn quite a bit. So even you go on, but thank you, that's an excellent question.
I mean, another question. I know that, or I assume that the Chicxulub impact has had an antipode event, probably a supervolcanic eruption. I thought I read that this was related to India, that there was a supervolcanic eruption after that.
Yes.
So the question, I mean, this 100 miles in the Nevada event is probably same size. So question, is there any evidence that there is, at that time, a super volcanic activity somewhere in the world?
So the question you've asked is a tricky one for a couple of different reasons. There is a war right now in thinking in geological sciences with one camp basically saying, yes, these appear to be related, and they worked backwards. They noticed that there was an impact, and then there were eruptions, and so they, you know, does correlation imply causation? So there are people who firmly believe that yes, the dynamics of what's happening here can trigger something down deep and end up triggering volcanism. It didn't cause it outright. You had to have the right pieces in place. You had to have something, but kind of nudge the light switch or something. The other camp says, no, there's no way. The Earth is enormous. This is a teeny tiny rock. It's big to us, very small to the Earth. So something all the way on the other side of the planet is not going to care that something like this happened, and it's certainly not strong enough to kick like an 80-mile pluton of lava into high gear from, you know, several thousand miles away. So there's good work being done on both sides. Personally, after reading it, I tend to lean toward asteroids still a little small to kickstart volcanism halfway across the world. But just like the weather system, there are lots of feedback systems in play that we haven't quite nailed down yet. Sure, I suppose you could have a domino effect that comes and ends up triggering something. But it has made people, there's even a third hypothesis that it's called a Vern shot event, where, and again, there's real science behind this. There's a guy who actually proposed that it wasn't an asteroid at all. That many times through history, you find big volcanic eruptions, and you find an impact crater. And he said, well, what if there's just a new kind of volcanism we never see, where you take a 40 mile thick piece of the Earth's crust, and he discovered there was some geochemistry going on where you can build up a lot of CO2, and it would stop and start pressurizing like you're shaking up a can of soda. And hypothetically, if that pressure got strong enough, you would break the 20-mile slug of rock sitting over top, and it basically becomes an Earth cannon firing, or an asteroid gun, because you would have a volcanic eruption here that shoots this enormous wad of crust halfway across the world and goes boom, and to them, it would look for all intents and purposes like an asteroid impact, right down to the iridium anomaly, because you're reaching down deep into the crust where you do have more of those metals. So that's an out there hypothesis, but he even admitted, to his credit, that It was just a hypothesis, and it was a little out there, but he pointed to what are the odds of a big eruption and an impact happening together over and over and over.
I mean, if this would be 280 million years ago, I mean, there should be some super volcanic evidence.
Yeah, and there is one. There's actually a mass extinction that happens 3 million years after this impact. But, that's enough time. Did it really relate? So there's a lot of debate going on right now, and there's good thinking on either side. So, like I said, I tend to lean toward it's coincidental.
So 3 million years is really sound, estimation.
Yes.
It's not saying...
Yeah, that the plus or minus on that is small enough where when people first found this impact, they thought maybe this is related to the extinction at the end of the Devonian. And then, in some cases grudgingly, they admitted, no, you know what, it's discrete. There's too much of a time separation between it and when mass extinction happens. But no, that's a very good question. But yeah, if you're interested, it's named after Jules Verne, cannon shot to space. So it would actually shoot the chunk out into space and land on the Earth again.
Well, a question along those same lines, is some of these arguments apply a coincidence between things, but if you're looking at time that far back, your noise has to be terrible for your resolution. And it's one thing to say something was within 2 years of something, and it's another thing to say it's within 20,000 years.
Right. I don't think reaching back that far, you find people, diving deeper than, a million years or several 100,000. But yes, you're absolutely right. Just for the reasons that you see looking at the Nevada map, it's tortured. All those rocks have been broken up and buried and changed, and so there are very few accessible spots. And even then, the error is pretty high. But there's also, and this is where I go to the biology, one of the big markers is there are specific kinds of conodonts. For some reason, these animals drop their teeth all over the place. So conodont teeth is a major way that geologists date things back in the Devonian. And they're distinct species that only happen in time ranges. So in a way, it's a small clock that showed up for us right there in that time period. So when you start looking at finer detail, usually it's conodonts, and it actually, the Alamo impact research used it because they found conodont teeth in a piece of breccia that had been ejected and landed. So they know how far down the original deposit had to be when the impact happened, because it took some of those teeth and buried them in a later time unit. So there's a lot of, this is the science of dating rocks is yawning and multifaceted. So there are a lot of tools, and no single tool is good, but together, you'd be surprised how close you can get. Thanks. All right, thank you very much for your time. Thank you for your testimony. If anyone wants to see the breccia, touch it, hold it, marvel, it's up here on the table.